Okay, so hopefully you guys did okay on chapter 11 with these videos. We're going to give it a shot with chapter 12. I know it's a bummer, but it's only 2 chapters. So again, you're always welcome to text me if you remind if you have questions on any of this. Okay? So to start off with chapter 12, this chapter is on regression. We're going back to the chapter 3 concepts from first semester, which is when we look at an explanatory variable with a response variable and looking at a least squares regression line. So we're actually going to start running confidence intervals and significance tests using that information. So here's an example to start us off with. Mrs. Blair wonders if a student's GPA is a good indicator of how well they will do on the ACT. She talks to the counselors and receives the ACT scores and GPAs of all seniors who took the test last year. She takes a random sample of 9 students. So if you remember, I know it's way back from the beginning of the year, but we need to find the least squares regression line for this sample data. So what I'm going to do is I'm going to plug this into my calculator. So you're going to see me switch screens. And I've got both calculators side by side because I don't remember how different they are. But for now, I'm just going to use this one. And I'm going to plug in my data. So I'm going to plug GPA into list 1, 2, 2.2, 2.3, 2.9, 3.3, 3.3, 3.6, 3.9, 4.1. So that in list 1, we have all of the GPAs. But then we need the GPA to match up with the ACT score. So we're going to say 14, 20, 20, 19, 19, 23, 22, 29, 32. Because again, we're trying to see if a student's GPA will be any kind of indicator on what they might do on the ACT. So you want these to pair up. Okay? So if you remember from the beginning of the year, in order to find a least squares regression line, we need to calculate that. So we're going to hit Stat. Scroll over to Calculate. You're going to scroll down to option 8, Linear Regression A plus BX. And so what I'm going to tell my calculator is I want it to do list 1, comma, list 2. All right? And so I guess I do remember the difference in here is when you go to the calculate and you go to option A, you would need to tell this calculator list 1, list 2, you want the frequency list empty, and the store you can leave empty, and you'd hit calculate. I haven't typed in the information into this calculator, but after you hit calculate, it'd show the same information. So as you can see here, it tells you the A, which if you remember is the y-intercept. The B is the slope. Those are the 2 main pieces of information I need. So I'm going to switch back to my other screen now, and let's write down the equation for the least squares regression line. I would say the predicted ACT score, remember the way we write that is with a hat, equals 3.57, which is the A in the calculator, plus 6.01 times the GPA, because remember your GPA is the explanatory variable. And if you remember the idea of this formula is A is the y-intercept, B is the slope, X is the explanatory, and Y is the predicted response variable. Okay, so that's what we're plugging in there. So, because this least squares regression line includes the data from a sample from the population, we call it a sample regression line. Remember, what we're usually doing is we're taking a sample to try to predict something about a population. This is not all of the students who took the ACT last year. It's a sample of 9. So because the sample of 9 students gives me this regression line, I call it a sample regression line. If Mrs. Blair took the time to input all of the GPA and ACT scores of all the students who took the test last year, then the least squares regression line would calculate the population regression line, which is it's kind of like the parameter. We're using a statistic to estimate a parameter, kind of like what we've been doing all year. So let's get to an interpretation. Again, if you kind of think about how we did this in the beginning of the year, interpret the slope we always want to say that for every increase of 1 unit on the explanatory variable, we predict the response variable to increase by the amount of the slope. So here's how I would say it in the context of this problem. In fact, I'll try and type it in. For every increase of, 1 GPA point, we predict an increase of 6.01 ACT points. So really, kind of what I'm talking about now is stuff that we did way back at the beginning of the year. Okay, so I know it's been a while. So for every increase of 1 explanatory GPA point, we predict, that's an important word to say, an increase of 6.01 ACT points. And that's because 6.01 was the slope. But again, the sample is what's helping us predict this. Now, the least squares regression line of the population regression line contain 2 parameters. Okay, and this is of the population line. That would be all the scores. The 2 parameters would be what we call alpha. Now, this is different than the cutoff level alpha that we've always used in significance tests. We say that this alpha is the true y-intercept. If you look back at the formula I used up here, instead of using an A, we just use alpha. We call that the parameter, the true y-intercept of the population regression line. And then instead of B, maybe you can guess, we use beta. This is the Greek letter beta. This would be the true slope of the population regression line. But again, the whole point of statistics is most of the time we don't have enough information to do the whole population. So instead we have to take a sample, which gives us a statistic. That statistic will estimate that parameter. So I'm going to introduce you to some new symbols. I mean, I've kind of shown you up here, but I'm going to kind of wrap it up here. So the idea here is the formula that we're used to using, y equals a plus bx, and you could even think of it as y hat, your predicted y. This is a sample regression line. That estimates the true regression line. We actually say it's the mean y equals alpha plus beta of x. So the true y-intercept plus the true slope. Okay? Now, on the sample regression line, remember that the A estimates the alpha. The B estimates the beta. And here's another one that we're going to have to use. The S, or what you're sometimes familiar with as S of x, estimates the true standard deviation. So remember that these here are what we call parameters. These are the true values. And these here are statistics. We use a statistic to estimate a parameter. Okay? So, in this section, we only care about the statistic B for slope. Because realistically, in these formulas, the B is the only one that really gives us much information. And if you go back to this interpretation of the slope, the slope is what gives us most of the information about the data. Most of the time, the y-intercept is an extrapolation anyway. So we're not really going to be testing the y-intercept. We're going to be testing out slope. So everything we do with regression will have to do with the statistic slope. Now, what was the slope from our sample? So go back up and look at the top. From the sample that we took, the slope was 6.01. So let's copy that down here. The slope was 6.01. If Mrs. Blair took a different sample, would she get the same slope? Why or why not? Hopefully you're thinking, no, I would not get the same slope. We already know that sampling variability plays a big part of this. So I'm just going to say due to sampling variability. We know that if we take many, many samples, the samples aren't all going to be the same. Hopefully they're close to each other, but they're not going to be exactly the same. But what if she took many, many, many samples? Well, what would get created if I took many, many samples? What we use all the time, a sampling distribution. So I'm going to take a picture. We know that we've got a curve here, but this is not going to be a sampling distribution of p hat or a sampling distribution of x bar. What this is a sampling distribution of b for slope, of all the different slopes. If I took many samples of regression, it would give me many slopes. So let's start with looking at the shape, center, and spread. Well, the shape would be approximately normal. And we'll get into the normal check, how we check for normality later, but it would indeed be a normal sampling distribution. The center, well, where do you think it's going to be centered around? Hopefully you're thinking what we've used in the past is always centered around the true value. Well, that's the case here, beta. It's centered around the true slope. So if I put that up here, the true slope is your mean. And then here is always the standard deviation. Well, again, we're going to be collecting this information from a sample. We're never going to know the true value. So when I say that, it's the standard error of the slope. That's what we call it, the standard error, which remember is the standard deviation formula just used with statistic information, not parameter information. So if we write that over here, we know that the center is centered at beta. Or in other words, you could say the mu of the b's is equal to beta. The spread is measured by the standard error, which is always using sample information. Standard error of the slope. Now there is a formula to use this. You're really probably never going to have to use this formula. Our calculator is going to do a lot of this work, but here's the formula. It's S, which is the standard deviation of the residuals, and I'll write that down in a second, divided by the standard deviation of X. This is the standard deviation of the explanatory variables, divided by the square root of n minus 1. I know it looks like a really complicated formula. So like I said, right here, this is the standard deviation of the x, which is the explanatory variable. So everything in list 1. So I could go to my calculator and I could do a one variable stats on list 1. Whatever the standard deviation of that is, that would be your S of x. The capital S up here, that is the standard deviation of the residuals, which remember a residual is the amount of error off of a line. So it's the standard deviation of the residuals divided by the standard deviation of the explanatory times the square root of n, which hopefully you remember is the sample size, minus 1. Okay? So I know this sounds really long and complicated, but really you guys probably will never have to use this. The calculator is going to do majority of the work for you. In fact, to find the standard deviation of the residuals, we do have this formula way back from the beginning of the year, which you're probably also never going to have to do. You take the sum of the residuals squared, and you divide by n minus 2. We did learn that way back at the beginning of the year, but we really didn't even use it then. We probably won't use it too much now. Okay? But the point that I'm getting at is that we are going to be testing a new statistic. We're so used to testing a proportion or a mean, but now we're going to be testing a slope. So in order to test a slope, we're going to have to use the sampling distribution of the slope. Again, the center is at the true slope. We have to use standard error of the slope, which is this crazy formula that I don't want you to worry about too much. But we are going to have this formula given to us by the calculator. That's going to be our standard deviation. Okay? So I'll let you click on the next video to see where we go from here.